Don't you just love particle projections? I spent a lot of time studying these and I was pretty sad when no questions like this came up in my stat paper, but what can you do? In this situation, it's pretty standard. There's no weird other forces or something acting on the particle. It just is what it is. It's just the standard projecting a particle from the origin question. So let's draw in our axis, y and x, and let's project a particle from the origin. And it's going to follow a basic parabolic path. There's my parabolic path. I hope you like it. And we start with speed. I'm going to say u, angle theta. And if you're familiar with parabolas and the path of projecting particles, there's a few standard things that we note here. So first of all, y double dot. That's the acceleration in the y direction. And that, of course, is minus g because the particle is under free fall. Y dot is going to be then, well, we integrate this, and of course our constant is the initial velocity, which is u sine theta. Take away gt. Then if we go here, integrate again, and we actually get a very familiar equation. Similarly for x, we see that, there's no force in the x direction, so that's fine. So x dot is just going to be constant, u cos theta, the resolve part of the initial velocity in that direction. And we see that x is going to be u cos theta times t. Now, in this particular question, we're told that the particle passes over two walls, which are horizontal distance d1 and d2 from the point of projection. So I'll ad hocly do this. d1. And let's say d2. Now the interesting thing is that the height that this particle will be at will be d2. And the height this will be at is d1. Okay, so that doesn't look very accurate in my diagram, but that's okay. Don't really care. Now we're asked to show, we want tan theta to be totally dependent on those distances, and we can do this. This is okay to derive. What we want here is, well, basically, if you've seen something like this before, if you see a tan theta in a projectile question, what this means is something called the equation of trajectory. And in order to get here, we need to eliminate everything except theta, basically. And our x and y will be our d's. So we're looking to eliminate velocity, time, g, all that stuff. So we're going to start with time, and we're going to get something called the equation of trajectory of the parabola. So I'm going to say t is x divided by u cos theta. And I'm going to sub that in to my equation for y. You may have seen this before, and if you have, you can, skip this bit. But when I sub t in, all I'm going to get, you can see here that the u's will cancel. And the sine and the cos will turn into a tan. So I get x tan theta. Then what's this bit? Well, our g over 2 times t squared. And again, this is gx squared. The u doesn't cancel this time, so it's 2u squared. On the bottom line, we have cos squared theta. Okay. Some people write that as sec squared on the top line here, and then they can expand that out to get tan squared theta plus 1 using the identity that that's equal to sec squared. But I'm not going to do that right now. Okay, so basically that's our equation of trajectory. Now we're told that the particle must be at this point and at this point and some point in our trajectory. What the equation of trajectory allows us to do is plug in different values for x and y at certain instances in the particle's path. So I'm going to use this on 2 occasions. And of course we know what occasions I'm going to use it on. So d1 will be equal to d2 tan theta minus g d2 squared over 2u squared cos squared theta. And then d2 is equal to d1 tan theta minus g d1 squared over 2u squared cos squared theta. All right, so what have I done so far in this question? I guess it was pretty intuitive up to this point. Like, you did what you would normally do. Given this problem, it makes sense to go to the equation of trajectory and plug things in. And if you've never seen the equation of trajectory before, well, now you have. So if a problem like this comes up, it's not that bad, So now, I guess what's left to do is, can we work out a way to eliminate g and u and anything else? So I just want the d1, d2, and tan theta. Well, if you think about it for a second, you'll see that there's a common part to both equations. It's basically this bit here, right? It'd be cool if I could make the subject. Kind of looks like a rubber duck. But it'd be cool if I could make that the subject. So basically what I want to do is, well, I can do that with both equations. If I bring this across here, and then I divide by this quantity, and do the same with the other equation, those rubber ducks there are equivalent. So if I take the top rubber duck, and I do this, I have this. And this must be equal to d2 minus d1 tan theta all over d1 squared. He looks pretty sleepy as well. I think the bottom one's like, I think the top one looks like really evil. The bottom one looks a bit like bloated. Okay, so we have this here. Now, okay, well, we're done basically. Hopefully this should lead us to the relationship that the question said. So I'm going to multiply across by this dude, multiply across by this dude here. So I'm going to d1 cubed minus d1 squared d2. I'm going to write tan theta as a capital T just for a second. And then I'm going to get d2 cubed minus d1 d2 squared T. And let's make T the subject. So I'm going to bring this guy over here. I'm going to bring the d2 over there. So I'm going to swap those two terms. I'm going to end up getting d1, d2, d1 minus d2 tan theta equals d1 cubed minus d2 cubed. And we're almost there. So, tan theta, I guess I'll write it as tan theta again now. Just didn't really want to write tan theta that many times. So, again, we employ just one more algebraic trick to solve this now. You look, and this is very, very close to what we want in the question, right? Very, very close. But what's missing? Well, it seems that even if you don't know this trick, you might intuitively get it. We want to basically hope that this guy here, we hope he divides the top line somehow. So this is called the difference of two cubes. You might want to remember this result, or at least know how to derive it for stat purposes. So it's just going to be this. It's actually used quite a lot. And you see that if we plug that in the top line, the bottom will cancel. Of course, provided one very important point there, that d1 does not equal d2. Okay. So we rule out that particular scenario, because if d1 equals d2, none of this really makes any sense. Okay, because we have we're using the same point twice, and we're not really getting much information. We couldn't. I mean, we're kind of dividing by 0 at some point there. So as long as you put that in, you're fine. So that was fun. Now what we want to do is find the range. So similarly, if you've done parabola questions before, the way to get the range is just, I guess, you want to find out when the vertical distance traveled is 0. So we want to set y equal to 0. And we see that there's two possible scenarios there. Either that will lead to t equals 0. But of course, that's trivial. That's just where it will start. So that'll be that solution there at the origin. Or if t is not 0, what equation are we solving then? Let me write it in green up here. Well, it'll be 0 equals u sine theta minus a half gt. Rearranging that, I will have the time at which the particle will have come back down. So it'll be the time of flight, I guess. So what is that going to be? That's going to be 2 u sine theta over g. Okay, now to get the range, I just want to find the distance it travels at that point. And of course, I'm going to use the equation here. These are pretty standard results if you're kind of used to this thing. So notice when I do that, I end up getting x is u squared. So that's 2u squared over g sine theta cos theta. Okay, and again, you can also spot that this is sine 2 theta, which we may or may not use. And it turns out in this particular instance, because we want the range to be independent of all terms except d1 and d2, I want to use a clever trick to eliminate the u's and the g's in one go. Of course, by looking at our rubber ducks there, we can do that. We would like a cos squared theta involved. So we're going to ad hocly make that so. So I'm going to write that as, I guess, cos squared over cos, which is nice because sine and cos equates to tan. Okay, so that's tan theta times 2u squared cos squared theta over g. That is our range, x. You could use a capital R if you wanted to. I guess it doesn't really matter. Is that exactly our rubber duck? Well, almost. It's like the inverse of the negative rubber duck or whatever. Yeah, I mean, you can just see clearly that, let's just do that precisely. It's d1 minus d2 tan theta over d2 squared. If I stick a minus sign in front of this and then I invert it, I have precisely that. Okay, so using notation or whatever, you can do that. So we're gonna get x is I'll write it in green, I guess. X is d2, oops. Yeah, no, that's right, d2 squared over d2 tan theta minus d1 tan theta. And we're basically done at this point. We just are reduced to simplifying I guess a rather complicated expression, if we're being honest. So what tricks could we employ to simplify this nicely? I don't know if I want to sub in the 2 tans straight away. That could get pretty messy, man. Any ideas would be welcome at this point from you guys. But I could just jump ahead and try and do this. Yeah, I don't really see another way other than just subbing in d immediately. I mean, I guess I could maybe write this as some like fraction, if that would cancel or whatever. Maybe no, I'm not really seeing a better way. Okay, so using tan theta, using the formula for tan theta, what was it? It was d1 squared plus I'm trying to remember that. Yeah, so d2 squared. Of course that's over, was it d1? I forgot, hang on. Yeah, d1, d2. What's that? I didn't really, I had no idea. And we're back. d1, d2. All right, over what exactly? Well, we're gonna have a negative d1 here. If I multiply it by d2, I'm just left with d1 squared plus d1 d2 plus d2 squared all over d1. So what I want to do is not have multiple fractions, first of all. That's not good. A number of things I could do. Let's cancel this d2 here. Multiply up by d1. So I'm going to multiply everything in this fraction by d1, which is good. So d2, d1 over, you see, we're going to have now the d1 squareds will cancel because this guy becomes a d1 squared, right? So that's d1, d2 plus d2 squared. That's going to be multiplied by yep, that's just d1 squared plus d1 d2 plus d2 squared all over just d1. And what happens now is these guys again cancel, and I guess that's correct. And not much else we can do there apart from, I guess, cancel another d2. There we go. And boy, that looks nice. And it's at this point where you probably say to yourself, that looks nice, like the right answer, because it's, you know, symmetric. It's a pretty cool result, actually. So that's really it. That was different than most mechanics step questions. They usually take me longer to think about, but I guess this one just turned out to be a little nice one, you know. You can never, I don't know, you can never really predict how hard a question is going to be when you start it. But yeah, guys, this is Chris here, and I'll see you next time. Hope you enjoyed that.